All right, this video is for AP Calculus, and we're going to talk about additional integration techniques that involve algebra manipulations of the integrand. So we have our shortcuts. Now we have integration by substitution, and we're going to learn some additional techniques later on. And sometimes you can just do algebra manipulations of various kinds on the integrand to put them in forms where those other techniques will work. So we're going to examine a few different techniques here. Here's one. So we have memorized this form that since the derivative of arctangent is 1 over 1 plus x squared, the antiderivative of 1 over 1 plus x squared is the arctangent of x plus c. But what if we needed to integrate this, 1 over 4 plus x squared? Could we do some algebra manipulation to get this 4 different in some way? And I think we can. Let's show you how we would do that. What we could do is say, well, we've got this 4, and I don't want it to be a 4, I want it to be a 1. So what if I just factored it out of the denominator here? That would put a 1 here. Then you would have x squared over 4 here. Okay? Which means that I could bring it outside of the entire integral and just make it 1/4 times this. But then this x squared over 4 could be written as x over 2 being squared, because the x squared produces x squared and the 2 squared produces the 4. And then I could do a u substitution. The u substitution would be, let's make that x over 2, or 1/2 x. The derivative here, du dx, would be a half. And then that means du would be 1/2 dx. And then we could start substituting. So I have 1/4. This is now 1 over 1 plus u squared. And this dx is 1/2. I'm sorry, wait. 2 du would be equal to dx. So this would be 2 du, right? And that means when I bring this out here, 2/4 is 1/2 integral 1 over 1 plus u squared du. And then we recognize that this is the form for arctangent, but this time it would be the arctangent of u plus c, which means when I substitute this back in, this is an indefinite integral, it would be arctangent 1/2 arctangent of x over 2 plus c. So you could use this shortcut by doing an algebra manipulation to get rid of the 4. But when you divide the 4 out, you also are dividing it out here, so it changes this and forces you to do a u substitution. Well, we could recognize something. We can say, hey, this number that ends up out here and here is just the square root of this number. So if I just thought of this as being 1 over 2 squared plus x squared, right? Then this ends up being that 1 over that 2, arctangent of that x over that 2. And you can just recognize that it's this pattern with this 2 filled in here. Right? So you can think of this as a more generic antiderivative. We know that the integral of 1 over 1 plus x squared is arctangent. So if you have, well, this is equivalent to saying the integral of 1 over a squared plus u squared du, if you move this du up here. So if you have an integral of 1 over a squared plus u squared, and that's going to be arctangent, but of this u divided by this a. And similarly, you can go through a similar situation to show that the more generic arc sign would be if instead of having a 1 minus u squared here, you have any constant squared, then this ends up being arc sign of this u over a, without the leading 1 over a. And if you have this structure, 1 over u times the square root of u squared minus a squared instead of a 1 there, then it's 1 over that a arcsecant of the absolute value of that u over a. We don't usually use the other versions because they turn out just to be the negatives. So personally, in the list of derivatives and antiderivative shortcuts, when it comes to antiderivatives, for the inverse trig functions, instead of just memorizing that arctangent is 1 over 1 plus x, I memorize that, we write this as 1 du here. 1 over a squared plus u squared. Instead of a 1, make that a generic constant a. 1 over a squared plus u squared is equal to 1 over a, arctangent of u over a. And same thing for arcsine and arcsecant. So you can augment your knowledge by taking the three that we're memorizing and write them in more generic forms. I would recommend memorizing this version over here. Okay, so let's do an example of that. Now that we have this kind of different form, I'm just going to say this. I'm going to have my toolkit again, and I'm going to say this form has to have a u here, which is a variable, and this a is a constant. Although not always true, lower letters of the alphabet typically represent constants, and higher letters in the alphabet, like X, Y, Z, W, U, things like that, those things usually represent variables. So the u represents a variable, but the a represents a constant. Right, so here we have an x, and that means that my u is x. This 4 has to be a squared, so that means my a is 2. So I'll identify that, and then I'm going to take a derivative here. Du dx equals 1, which means du equals dx. And now I can substitute in this integral. This is now 1 over a squared plus u squared, and this dx is du. And this is the form that we're going to memorize as 1 over a arctangent of u over a plus c, and now I just substitute 2 in for that a, and x in for that u and 2 in for that a, and I get the same thing I did it here, but without having to do all of the algebra manipulation that we did over there. All right, so that's how we can use these more generic inverse trig integrals. All right, so let's try something else here. Sometimes a u substitution won't work as initially stated, but we can split the integral into multiple integrals. So, like if I'm going to do a u substitution with 4 minus x squared here, that means that the derivative du dx is going to be negative 2x, so we have du is equal to negative 2x dx. That means I need an x, and it's here, but I've got this extra 2 hanging out here. Right, so what can we do about that? Well, what we could do is split this integral into separate integrals, because this is all a common denominator, and then the numerator is separated by a plus. So what I could do is separate this into two integrals. This is equivalent to x over that square root of 4 minus x squared dx plus a separate integral with 2 over that common denominator. Okay, now why does this help? Because in this version over here, we can do this u substitution. So for this, I'm declaring u to be 4 minus x squared. So the derivative du dx is negative 2x. So du is negative 2x dx. And therefore x dx is negative 1/2 du. And then I can substitute this and say this is 1 over the square root of u, and that x dx is negative 1/2 du. Which means I can write this as negative 1/2 integral u to the negative 1/2 du. And then I can take the antiderivative. If I add 1 to negative 1/2, I get positive 1/2 divided by 1/2 plus the c. I'll wait and put the plus c on it here. Right, so then we've got 1/2 divided by 1/2 is a 1, so it's negative, and then this u is 4 minus x squared, and then to the 1/2 power. So by splitting this up, we can get the x by itself that we need to make u substitution work. But what about this one? Well, for this one, we can move the 2 outside here. And I've got 1 over the square root of, and I'm going to write that as 2 squared minus x squared, because that matches my form for arcsine. So over here, I'm going to define u as x and a as 2. Take the derivative, so du dx in this version is 1, so du is dx, which means this is 2, and then we have an integral of 1 over, now this is the square root of a squared minus u squared du. And that means that we can use that arcsine shortcut. Now that one does not have the 1 over a, so it's just arcsine of the u, which is x, over the a, which is 2. Then I'm just going to add these two things together and put the plus c on, and I'm done. I might change this to a square root to make it match. So this if you need to see it again, pause that video and rewind it and watch that again. Try it on your own, because this is an important idea to master. The idea that you can split a common denominator into multiple integrals and maybe use two different techniques for each. Like we used U substitution over here, and we used an inverse trig substitution over here. Okay, so here's another technique, an old algebra technique called completing the square. So the way completing the square works is, let's say we have x plus 3 squared. That's a perfect square. That's x plus 3 times x plus 3, which means if you do FOIL, it's x squared plus 3x plus 3x plus 9. And that means it's x squared plus 6x plus 9. This and this are equivalent, they're just in different forms. And this is called a perfect trinomial. But what I want you to notice is that this number here, this 3, is half as big as this number, and this number out here is this number squared. That's always true. So what we can do is, when something isn't a perfect trinomial, we can force it to be a perfect trinomial so that we can at least take part of this and write it in this perfect square form. Okay, so here's how that would work for this, x squared minus 4x plus 7. What we'll do is we'll take the x squared minus 4x and leave a little space here for the plus 7. And we're going to try to make this a perfect trinomial that we can rewrite as a perfect square. So I'm going to copy this x here, and then I'm going to take this negative 4, so this 4 with this minus sign, and divide it in 2, because this number is half of this number. So I'm going to take this negative 4 and divide by 2, and then I'm going to square that number and put plus 4 there, because this and this are now equivalent. But you can't just go adding a plus 4 unless you subtract it back off so that it's not changed. Now we have a new number out here. That means this and this are equal. Now why would that be helpful? Because if you have an integrand like this, then you can do the completing the square procedure that we just did and found that this is equal to x minus 2 squared plus 3. Let me just do it again. And you can practice this with me. Maybe pause the video and complete the square over here. Change the size again. Minus 4x plus 7. The way we would do that is leave a little space. Make this x, cut this in half to negative 2. Square that number. I'm underlining it because I added it, so I have to subtract it back off, which gives me plus 3 there. Now I'm going to replace the denominator of this integral with x minus 2 squared plus 3, because that's equivalent to that. But this, if I define u to be x minus 2 and a to be the square root of 3, and therefore du dx is 1, so u equals dx, I can now rewrite this as, write it a couple ways here. I'm going to reverse these, and I'm going to write this as the square root of 3 squared plus x minus 2 squared, so that I can write this as now 1 over a squared plus u squared du. And we know that this is 1 over a times the arctangent of u over a plus a c. So for my toolkit, my a is the square root of 3, so 1 over the square root of 3, arctangent of u, which is x minus 2 over the square root of 3, that's the a, plus the c, and we're done. So this is fairly frequently found on the AP exam, and we call this completing the square to arctangent form. Because if you complete the square, you're going to get something with an x squared at a constant squared, and as long as that's a plus, it's not always a plus, but if it happens to be a plus, it means you're going to be able to solve this by making it match the arctangent form. So I know these seem very arbitrary, and they are. This is kind of everything in the kitchen sink here. We're just throwing a bunch of different techniques that you might see that are useful to know, that involve algebraic manipulations or other manipulations. So notice that this will only work when the denominator is not factorable. I don't think we will typically be able to do that in a case like this. Actually, could we do it? Let's just see. Could we complete the square on this? That would give me x minus a half. And then, let's see, if we squared that, that would be 1/4, and we would balance that with a negative 1/4. So this might still work. No, actually it won't work. Here's why. Because Negative 6 minus a fourth is the same as negative 24 fourths minus 1/4, which is negative 25 fourths. So it would give me negative 25 fourths. Okay? But if we were to replace this, this would be x minus 1/2 squared minus 25 fourths. So when things are factorable like this, often we have a negative sign here, and that means it's not matching the arctangent form. Because the arctangent form, we have to have a plus there. So there are other techniques, and we're going to learn another one later called partial fraction expansion that will work better than completing the square. And it'll work for both positive and negative cases, but it only works when the denominator is factorable. So we complete the square when it's not factorable, and we have a future technique that we use if this is factorable. Because actually, you could factor this x squared minus x minus 6 into x, let's see, plus 3x minus, no, x minus 3x plus 2, right? So what this is equal to is the integral of 1 over x minus 3x plus 2, right? This denominator was not factorable, so we had to complete the square. This one is factorable, so we're going to have a different technique for later. So we'll talk about how to handle that case later on. Okay. Here's another one. What would we do for this one? It's from our extra practice packet if you're in our class here. So this is not obvious at all. It's a quadratic on the bottom, but it doesn't have 3 terms. So what we could do for this is we could do polynomial division. This is a division problem. So in Honors Algebra 2 or equivalent course, you should have been taught how to divide x squared plus 1 into 3x squared minus 2x plus 3. So let's try just doing this as a division problem. The way that works is you say, what would I have to multiply this by to get this? And that would be a 3, because it's already a square. So in the numbers here, if I just put 3, and I multiply that, that's 3 times x squared is 3x squared. 3 times 1 is 3. And I'm going to subtract this from that. So this minus this is nothing. Negative 2x minus nothing is negative 2x, and 3 minus 3. So the result is that this division problem, 3x squared minus 2x plus 3 over x squared plus 1, is 3, but it's got what we call a remainder. And so we add it this way, plus the remainder 2x over x squared plus 1. So we can just go ahead and divide this, and what we would get is that integrand gets replaced with 3 plus negative 2x over x squared plus 1, which means we can separate this into 2 integrals. So we can say it's the integral for 3, and it's going to be minus the integral. I'm going to move the negative. I'm going to move the 2 down here. No, I'll leave that up there. So 2x x squared plus 1. So I'm taking the negative only and moving it down, right? This one over here can be done with u substitution. Because if I make the entire denominator the u, then the derivative would be 2x. So du is 2x dx. And that means that I can say this is 1 over u. And then this 2x dx here is just the du. Okay, so this is another thing that happens with u substitution. We didn't see it in the u substitution video very often. If you can't clearly identify a function inside of another function, right? If you have a fraction, that fraction itself is the function 1 over x. So you can try the entire denominator as the u. Because now, what is the antiderivative of 1 over u? It's natural log of the absolute value of the u. So therefore, it's natural log of the absolute value of x squared plus 1. And for this integral over here, that's just an integral of a constant. So the result of that is 3 times the variable. And then we tack on our plus c, and we're done. So the point is, we can do the algebra technique polynomial division with the remainder, and just write that result, replace the integrand with that, split it into 2 integrals, and maybe a technique like u substitution will work on one, and a shortcut will work on the other. Okay, the last thing we're going to include here are a couple of examples related to trigonometry. So these are not really algebraic substitutions, but there are some kind of simple substitutions we can do that will work. We're going to cover trigonometry integrals more formally in a later section here, but to give you kind of a preview of that, we know that tangent of any angle is equal to the sine of that angle divided by the cosine of that angle, or we should have that memorized, that reciprocal identity. So that means that we can replace this tangent of 2x with sine of 2x over cosine of 2x. Right? And then I can think of one of these two functions as being inside. This cosine of 2x is inside a 1 over x function. So I'm going to make that entire denominator the u. And then I'm going to take the derivative, du dx, do a u substitution. So the derivative of cosine is negative sine. And then by the chain rule, the derivative of the inside is 2. And that means that du is negative 2 times sine of 2x times dx. And so that means I can rewrite this as we have 1 over cosine of 2x. And then we've got this sine of 2x dx, which means this becomes 1 over u. And the sine of x 2x here is equivalent to negative 1/2 du. So we put the negative 1/2 out there and the du here. And that means that this is negative 1/2. The antiderivative of that is natural log of u plus the c. So it's negative 1/2 natural log of the absolute value of cosine of 2x plus the c. So you can replace tangents with sines over cosines and then use the denominator as a u. Could you do that with something more complicated like this? I think we can, because the derivative of this inside function x to the 4th is going to be x cubed, and we're going to need that as well. So maybe I can do this. Let's do that same idea with the tangent. So let's say this is, I'll move this x squared over here. So this tangent, I'm going to replace it as sine of x to the 4th over cosine of x to the 4th. And I've got my x cubed dx. Then I'm going to declare this cosine in the denominator as the u. This time it's cosine of x to the 4th. So the derivative would be negative sine of x to the 4th times the derivative of the inside, which is 4x cubed, which means that du is negative 4 times sine of x to the 4th times x cubed dx. So that means that if I rewrite this like this, 1 over cosine of x to the 4th, and I'm going to bring this down, so this is sine of x to the 4th times x cubed times dx. That's right here, so if I divide by negative 4, I get negative 1/4 du is equal to that sine of x to the 4th times x cubed dx, which means this whole thing is going to be replaced with du, or negative 1/4 du. So now I'll replace the cosine with u. This gets replaced with negative 1/4 du. The negative 1/4 comes outside. We do the antiderivative of 1 over u, which is natural log of u. And then we substitute cosine of x to the 4th in there. And that's the result. So tangents could be replaced with sines over cosines, and then you can make the cosine in the denominator the u for a u substitution. That will work really nicely. Like I said, we're going to have a whole lesson just on dealing with more complicated structures with trig, but for right now, we'll just know that tangent can be manipulated that way. I would say you should start, if you haven't forgotten these things, memorizing a few things related to trigonometry. You should memorize that tangent is sine over cosine, and cotangent is 1 over tangent, so it's cosine over sine. You should know things like the cosecant is 1 over the sine, secant is 1 over cosine, cotangent is 1 over tangent. The way I remember that is in each pair, only one of them has a co in it. So cosecant goes with sine, but secant goes with cosine. And then you should know the Pythagorean identity. Sine squared of anything plus cosine squared equals 1. And you can convert these into these other forms. Like if you take sine squared plus cosine squared equals 1, and you divide everything by a cosine squared, then you get sine over cosine, which is tangent squared, plus 1 equals 1 over cosine, which is secant squared. So if you divide by cosine squared, you get this version, and if you divide everything by sine squared, you get this version. Later, we're going to need these as well. that sine squared of x is 1 minus cosine of 2x over 2, and cosine squared is 1 plus cosine of 2x over 2. And we're going to need that the sine of 2x is 2 times sine times cosine. These leave for later. We'll talk about those more later. But I would start memorizing these now, because we'll reduce the amount of stuff we have to memorize later. All right, one last idea to tie up this video. This is pretty rare, but something that we do see, and we occasionally need this in Calc 3 or ideas related to this. So let's say we had this, 1 over 1 plus e to the x. If you try to do a use substitution with the whole denominator there, what would that be? Well, the derivative of this would be the e to the x. So that means for use substitution to work, I'm going to need to have an e to the x in this numerator. So what I could do is I could force there to be one there, but in a weird way. I've already got this, 1 over 1 plus e to the x. So what I'm going to do is I'm going to add and subtract an e to the x. I'm just going to go ahead and put plus e to the x minus e to the x. If you add and subtract the same thing, you're actually adding nothing. But that's going to allow me to split this into two integrals. So one of the integrals is going to be this part. So it's going to be an integral of 1 plus e to the x over that common denominator of 1 plus e to the x. And then I've got minus the other integral, which is e to the x over 1 plus e to the x. Okay, on this one, we have the e to the x that we need for u substitution to work. Because now this is 1 over this u, and this e to the x dx is the du, which means that this is the natural log of u, which is negative natural log of 1 plus e to the x. Now what about this? Well, 1 plus x over 1 plus x is just 1, which means the antiderivative of that is simply x. And we add our c, and we're done. So tuck away in your brain for later that another algebra manipulation is if you need something in the numerator to make du, you can just add it and subtract it back off, and it'll be there in one of the two integrals when we split them apart like that. All right, tricky. All right, that will be it for the algebra manipulations. Next up, in the next video, we're going to talk about integration by parts, which is another major procedure. But we do encounter algebra fairly frequently.